Assalamualaikum and very good morning. We are from Think Tank Company and our project is about production of methanol from carbon dioxide. So my name is Nur Sazwani binti Rosli. My metric number is 188323. So I'm going to explain the first three unit operation. For the first one is electrolysis. So in the electrolysis about 190 kilogram, 19,000 kilogram H2O is being fed into the electrolysis and then produce three different material, which is H2O, H2 and O2. So only H2 is being transferred to mixture while the other two is being removed. So in this process, in this unit of, we use the pressure is 1 atm and the temperature is 30 degrees Celsius. So our heat transfer is about 30141959.93 kilojoule. So we proceed to the next unit operation, which is mixer. In mixer, we fed the raw material, which is CO2. It's about 100 kilogram, 100,000 kilogram of CO2 is being fed, and also the H2 from the electrolysis. And then the mass flow rate is about 1138197.15 kilogram in the one mixture. So in this operation, our PATM is 1 atm and the temperature out is 30. But in the raw material, carbon dioxide, the temperature that being used is 25 degrees Celsius. So the heat transfer is about negative 8936796.669 kilojoule. So we proceed to the next unit operation, which is compressor number 1. So the input and output, the molar mass of molar flow rate for the input and output is same because it's maintained, and then the temperature is being maintained, which is 30 degrees Celsius, but the pressure is being increased from 1 atm to 50 bar or 49.35 atm. So in this process, it doesn't have enthalpy, but we have a work shaft. So heat transfer is heat transfer equal to work shaft, which is 2231.397.662 kilojoule. Okay, that's all.
Moving on to the next unit, which is the heater. The heater functions to heat the reactants, which are carbon dioxide and hydrogen, to 240 degrees. The heater, so for the heater energy balance calculations, we have used CO2 and H2 as a reference states, and some of the values can be calculated from table V.8. But for the change in pressure at a constant temperature, we have to use this equation, which was given by our friend from our class and was approved by the lecturer. This equation, for this equation to be used, A and B must be found. A and B can be found using this formula here. So T and P here are critical temperature and pressure. So actually this heater functions using electricity. So if it's electricity and this is the much of electricity that is used in this heater. Next, moving on to the reactor, methanol reactor. These are the basic informations for the methanol reactor. And after that, there are a few other reactions. Heat of and before that I want to state the method used to solve this energy balance. First, heat of formation of method is used, and reference state elemental species 180 and 25 degrees Celsius. So the heat are calculated H1 to H6 as stated here. I'm stated in the table correctly. And after that, we just found that the reaction is exothermic. If you are confused, why am I not putting inside the table? Because I have directly multiplied the number of mole into the heat of reaction. So that it's the same. But so I hope you don't mind and it's easy to understand. Sorry for the inconvenience. Next, moving to the heat exchanger. Actually, there should be an arrow here for the mass of water. I will forget. I will put it. Don't worry. In the next update, I'm very sorry. Okay, okay. Now is okay. The heat exchanger. The heat exchanger functions to lower the temperature of the reactant's effluent to about 80 degrees, so that it is 80 degrees when it reaches the flash separator. So for the energy balance, I have used carbon dioxide, hydrogen, and CO at their 25 degrees and 180 atm as their reference state, methanol at 80 degrees, liquid at 45 bar, and water at triple point. So the same concept is used, the energy balance concept, with the non-reactive one. So I have calculated the H, and the Q here is negative. So the Q here is negative. So the Q heat released here must be absorbed by the coolant. In this case, the coolant we are using is the water. So when we are using the water, so we must find the mass of water or the flow rate of water per year. So then I found it using the normal M times heat, or specific M times H, H water at 37 degrees Celsius and H at water 25 degrees Celsius, which can be found from table B point 5 6, I think, and 5, table B point 6, yeah. So based on that, I found the number of kg of water needed per year, and the volume is stated as here for 1 year, because we have to have m cube, the unit in m cube, so that we can find the volume. I mean the cost using this tariff. So thank you. That's all from me.
Okay, hi everyone. My name is Farah, and today I'm going to explain more on flash separator, which works as a separator that will separate liquid and vapor streams. For the liquid streams, this one, it will go to the distillation column, and no, first it will go to the compressor first, and then it will go to the distillation column. And for the vapor stream, we will delete all of them. And then this is the composition of the substances in the liquid stream. You can see that methanol has 0.3137 mole in the liquid stream, and the rest will be at the vapor stream, which is 0.0022. It's very small because we want all the methanol and water to be at the liquid stream, because it's very important if we have major of it in the liquid stream. So I have calculated the energy balance. This one is the table, and this is the reference state that I have written down in it. 25 degrees Celsius, I use it, and this is the table where I refer on. Boiling point, heat of vaporization, PC, PC. For PC and PC, I use it for calculating the change in pressure. This one, maybe it's too small, so I'll zoom in. So this is for the methanol from 44.41 atm to 1 atm. So we have to calculate the A and B. Where do I get this one? So I use a formula, and the formula is, as you can see, I didn't write down the formula, and debugger did it. Let me show you. Okay, this one is the formula where I use to calculate the change in pressure. So I've got this one, and we have to make it per mole. So I divide it with the mole of methanol, the mole of water, this one is the value, and the mole of carbon dioxide, and the rest. And this one is the change in temperature. So I use heat capacity that I've got in the book, table table B2, I guess. So this one is the value, this is all the values. Okay, this is for the inlet stream. For the outlet stream, this is the pathway. Okay. For example, is the CO2 from 4.24 atm. I have to change it to 1 atm to ease the calculation. So I use the previous formula, and then I use the capacity for changing the 25 degrees Celsius to 80 degrees Celsius, and then I have to change back the pressure to 4.24 atm, like this. So this one is the same as before. I use the same formula to calculate the energy. So all of these are the same, but not for methanol. The first one is from the vapor to the liquid stream. So this is the pathway of the methanol from 4.24 atm to 1 atm. This is the same as before. And then from 25 to its boiling point, because it will change the phase, right? So we have to do it from 25 to its boiling point. For all the substances that we have to change the phase, we have to go for the boiling point, and then we have to add the heat of vaporization, which is from vapor to liquid, and then from boiling point to 80 degrees Celsius, and then from 1 atm to 4.4. Okay, these are all the same. So this is the energy balance. Basically, we have to divide mole and the enthalpy change, and then sum all of it minus the inlet stream. Okay, this is for the flash separator, and then we have to look at the compressor. The compressor, we have to calculate the shaft work. So using the shaft work, basically all the compositions in the inlet stream is the same as the outlet stream. So this is the energy balance calculation. For the inlet, yeah, this is the formula. We have to use the inlet pressure, and for the outlet, we have to use the outlet pressure. It is just like that. So this is the energy balance, but it is in joule. So I have to calculate that lah to make it in kilojoule. So this is the energy balance. Okay, that's all for my part. Thank you.
Hello, my name is Arina Ofa, and today I will explain to you about my part in this energy balance calculation, which is in the distillation column and also costing. For distillation column, we have N12 as the feed and N14 and N13 as the outlet. Okay, in the N12 we can see we have methanol and water and other substances, with mole fraction of 0.3 for methanol, water is 0.39 and other substances is 0.25. With the total flow rate, the total flow rate of mole is, this is mole flow rate with 15,398, and then the outlet stream is N14 and N13. So as we can see, N13 we have 5,886 kilomole flow rate, kilomole per hour, and we also have 9,453 kilomole per hour in the outlet stream. And this is the mole fraction for the outlet in N13 and the mole fraction in the N14. So for this energy balance, I calculate, we need to calculate the number of heat for this reaction that happened in this distillation column. So I use reference methanol as liquid, 80 Celsius and 8.5 atm, and water at liquid form at for 25 Celsius at 8.5 atm, and for carbon dioxide, which is vapor, 25 Celsius 1 atm, and carbon monoxide in vapor form at 25 Celsius and 1 atm, and this is not included. CO2, I think this is H2. This is for H2. Okay, in the vapor and 25 Celsius and 1 atm. And then I calculate the H in and H out for this reaction that happened in the distillation column. Distillation column is a non-reactive calculation, so I use the V changes of pressure and also integration of Cp, and I calculated all of it, and I get the total is 1573 kilojoule per hour per year, kilojoule per year. Okay, for the costing, this is the water price. It's RM 2 ringgit per meter cube, and then on the monthly basis we have raw material and coolant, and this is the cost. This is this total we get from our calculation. For this raw material we have carbon dioxide, water and catalyst, and this is the cost for 1 year. And then for monthly basis for TNB, which is the electric, this is the amount of industrial tariff. So monthly we use 724 kilowatt per hour, and cost for 1 month is only RM 266. Also we have utilities such as electricity and water coolant as we calculated here. And then our total operating cost with catalyst is 70,205, and total cost with catalyst high is 109,805, and this is the total operating cost. So our product with methanol per million ton, for low price we can sell, the selling price is $460, and for high price is $496. So the selling price per year we get $322,623, and also for high price we get $347,871. Catalyst lifespan is 4 years based on our journal. So this is our cash flow as you can see here. Okay, that's all from me. Thank you.